Hi everybody, Captain Al speaking with your training tips designed to help make you a better, more knowledgeable flight simmer, pilot, or aviation enthusiast. Let's strap in and stow the HUD and see what is on the horizon for today. Our briefing today will cover thrust limits of the 747-400 and 747-8. A lot of the times it's not necessary to use maximum takeoff thrust when the takeoff is not at the maximum allowable takeoff weight. So if we're at a weight that allows a reduction of thrust, we'll utilize that because most of the wear on the engine occurs during takeoff. When you operate at a lower takeoff thrust level, you use less than the full takeoff thrust rating. This does a couple things. It lowers the turbine inlet temperatures and it increases the engine's life and saves money. The result of reduced thrust operations are increased engine reliability because you're operating at a less of a power setting than full takeoff thrust. You increase dispatch reliability for the airline. You decrease engine operating costs, and you decrease engine maintenance costs. There are two methods for thrust reduction. One is the Fixed Derate Method, and the other one is the Assumed Temperature Method. The Fixed Derate is one way to operate an engine at less than full rated takeoff thrust. When you operate at a fixed derate, it's like having a less powerful engine. Because the derate is a separate thrust rating, each derate thrust level will have its own set of performance charts in the airplane flight manual or in your specific airline's performance engineering. Typically, they're color-coded charts. So they may be a certain color. There's a way to differentiate between TO1 and TO2. If you take off with a fixed derate, the derated thrust level is considered a new maximum and should not be exceeded. Similar to reduced thrust, the ATM method, the derate may be used when the takeoff weight is low enough to permit the use of a derate. When you use a fixed derate, all of the performance information is calculated at the lower takeoff thrust rating. Therefore, your VMCG will be lower. One advantage of fixed derate is it can be used to increase the performance limited weight when the runway is short or it's contaminated with standing water, slush, or ice. The Boeing fixed derates are TO1 and TO2, and they're at 10% than full rated thrust for TO1 and 20% less than full rated thrust for TO2. This is adjustable to meet airline requirements, so it's customizable. Some airlines may not want 10 and 20%. They may want 8 and 18% or something different. So this is fully customizable based on an airline's requirements and what they want for their performance requirements and the charting that they're going to use. The other method is the assumed temperature method, sometimes called the flex method. Takeoff performance for the assumed temperature method are calculated by commanding the engine to mimic thrust produced as if the outside air temperature is actually higher than it actually is. A fixed derate takeoff basically tells the engine to pretend through a lower rated thrust setting that it is a weaker engine than it actually is. So there's a difference in how it reduces the thrust. And in case of the ATM, it's by temperature, pretending it's warmer than it actually is. With a fixed derate, we're actually having a lower rated thrust setting, and we're, again, pretending that the engine is actually weaker than it actually is. The assumed temperature method is used by setting a takeoff thrust by entering into the FMC a temperature that is higher than the actual temperature. So if the temperature, outside air temperature is 5 degrees centigrade, we may enter a 45 degrees centigrade temperature to tell the engine that the temperature is 45 and the thrust would be reduced proportionate to the temperature being a much higher temperature than it actually is. Here's an example of a runway analysis chart for Seattle-Tacoma, runway 16 left. The outside air temperature is currently 20 degrees centigrade. We're in the 400 freighter and the wind is 160 at 10 knots. So you can see for 20 degrees, which is our current temperature, the maximum allowable takeoff weight would be 407,000 kilograms. But we weigh 360,000 kilograms. So we can go up the chart, like you see with the blue arrow, to where we would be able to use a 360,000 kilogram takeoff. And so the max there would be at 361,600 pounds. So we were under that. And then we'd come across to the temperature, and that would be our calculated temperature for the assumed temperature method, which would be 48. So by putting 48 into the FMC, we're pretending that, again, it's a warmer day than it actually is based on our current weight, which is less than the max allowable takeoff weight. And so we can reduce the thrust on that engine for takeoff, which again saves money, reduces the wear and tear on the engine for takeoff. Both assumed temperature method and the fixed derate takeoff method result in a takeoff thrust that is lower than 100% power. So what are the differences and the limitations of each? Well, the difference really is in the minimum control speeds, your VMCG and VMCA. In the assumed temperature method, pilots are allowed to advance the thrust levers to full takeoff thrust if it is required. Now, most of the time it shouldn't be required, but if it is required in like an emergency, you could advance the thrust levers using the assumed temperature method, because the assumed temperature method is based on the VMCA and VMCG being based on full takeoff thrust. Whereas in a fixed derate, the thrust levers should not be advanced beyond the fixed derate thrust limit. Otherwise, if you had an engine failure, that could cause a loss of directional control because the VMCA is calculated at the lower thrust setting and not at a full takeoff thrust setting like the ATM is. Fixed derate is considered a limitation for takeoff because you are reducing the rated thrust. Takeoff speeds consider ground and air minimum control speeds at the fixed derate level of thrust. And that's the reason why you can't, or you shouldn't, advance the thrust beyond TO1 or TO2 in other than an emergency. If you had to, you have to, but the thing you're concerned about is if you lose an engine, then and you're at a higher thrust setting than the fixed derate, you may have control issues. The assumed temperature method can be used on a wet runway. It's okay as long as performance data is used for a wet runway. Assumed temperature method is not permitted on a contaminated runway. The minimum controllable speeds are calculated based on the full rated takeoff thrust when you're using assumed temperature. And there's no guarantee of sufficient directional control that can be maintained on a slippery runway, thus it's not allowed. So that's why we cannot take off on a contaminated runway using assumed temperature, because there's no guarantee that you can maintain directional control once you start slipping and sliding. For the fixed derate method, you can use charts that will allow you to use for a wet runway or a contaminated runway, as long as you meet the particular weight requirements for that. If performance data is used for wet contaminated runway, it's based on the fixed derate being used. If you're on a slippery runway, the minimum control speeds are calculated at the lower thrust setting. And again, not so with the ATM method, which is why there's no guarantee that you can maintain controllability on a contaminated or slippery runway. Okay, we're in the 747-8 simulator. The thrust limit page is up on the CDU. One thing to consider on the Dash 8 is that the CDU pre-flight is slightly different in the sense that when you go to the takeoff reference page, you're going to notice that there are two pages, page 1 of 2 and page 2 of 2. In the 400, we only had one takeoff reference page. In the Dash 8, we have two. And you always want to fill out page 2 first, and then go to page 1 and fill that out. Now, the reason being because if you fill out page 1 first, then go to page 2, and you put things in page 2, it's going to dump out things in page 1. So in order to get our V speeds and to activate our V speeds, we want to go to page 2. Reference outside air temperature is 0. That's at current Minneapolis temperature. Wind is 340 at 12. And the engine out acceleration height is 1,000. Acceleration height is 1,000, and thrust reduction is flaps 5. We'll stay with that. We'll make these big. You don't have to, but I like to just because they stand out. That's NADP2, which is fine for our training flight. And once we've got this information in, then we can go back to page 1, fill out page 1, flap 10 takeoff. CG is 25%. And then we can activate our V speeds. You know what, we're not going to do that yet because we're going to be changing our thrust a little bit here. So let's go back to the thrust limit page and take a look at this. On the thrust limit page, you have your outside air temperature, which is currently 0 and 0. And you can see that the max takeoff N1 is 95.7%. That's the green hash mark that goes across all 4 engines. You'll notice there is a little amber hash mark that also goes across all 4 engines, and that would be the maximum N1 given today's conditions. So since the default is full takeoff and full climb, that would give us the maximum that we could use for this particular day based on the environmental factors that we have. Now, of course, we can take off with full takeoff thrust, but if we're at a weight that allows a reduced thrust, we'd rather use reduced thrust because it saves engine wear and tear. So we have two methods, the assumed temperature method and the fixed derate method of reducing the thrust. With the fixed derate method, you've got TO1 and TO2 in addition to full TO. TO1 is 10% less than full rated thrust. TO2 is 20% less than full rated thrust. Those are the Boeing defaults. Airlines can modify that as they choose based on the charts that they have, based on their performance engineering. So they may not want TO1 to be 10%, maybe they want it to be 8%. TO2, they may not want 20%, they may want it to be 18%. So these are modifiable, assuming that they have the proper performance engineering charts for TO1 and TO2 based on that reduced thrust that they choose. You'll notice if we select TO1, it's not only going to select TO1, but it also selects Climb 1. It'll automatically default to the appropriate derated climb. Now, we don't have to stay with this if we don't want to. If we don't want Climb 1 thrust, we could always change it to Climb and or Climb 2. You can change this thrust as appropriate. But whenever you select it, like TO2, it'll go to Climb 2. But again, if we don't want that, we can change it to Climb. You'll notice when we select TO2, the TO2 max N1 is now 87.4%. You notice the green solid lines, the hash marks have come down. They're at 87.4% now. The amber lines would represent that max N1 of 95% that we saw before. One thing you should be aware of is that the max thrust reduction available is at 25% less than full rated thrust. You can't reduce below 25%, so no matter what we do here, the thrust can only reduce a maximum of 25%. If we go back to full TO thrust and we want to use the assumed temperature method, then we could select a temperature and put it into one left, and that would pretend that the temperature is actually warmer than it actually is. So right now our temperature is 0. If we put 52 in there and we put it to the select line, we're now pretending that for the engine's sake that it's a warmer day than it actually is, and the thrust will be reduced. You'll notice over here it's derated takeoff thrust, 52 centigrade, 88.7% is the N1. That's where the green hash marks are. And you'll notice in this case that climb 1 has been armed. That tells us something. That tells us that the thrust is between 5 and 15% reduction from the full rated thrust. If it were to arm climb, we would know it's less than 5% rated thrust. And if it were to arm climb 2, we would know that the thrust is rated or has been derated more than 15%. So climb would be less than 5%. Climb 1 would be between 5 and 15% less than full rated thrust. And climb 2 would be more than 15% reduction in thrust down to a maximum of 25 degrees or 25% of rated thrust. In this case, if we change this to 30 degrees instead of 52, you'll notice that climb is now armed instead of climb 1. And that's telling us the thrust has been reduced by less than 5%. And again, that makes sense because the temperature is 0. We're pretending it's 30 degrees. You can see that the thrust has been reduced slightly down to 92%. And remember, with full takeoff, it was about 95%. So for purposes of today, we're going to put in 52. And by the way, we can use also, if we have the charts for it, we can use TO1 thrust and an assumed temperature together. So if we were to do that, TO1 reduces it by 10%. The 52 centigrade reduces it even further. It arms climb 2, so we know that the thrust is reduced more than 15%, but not more than 25%. Notice every time we select thrust, it's going to kick out the temperature. We'll go back to full TO, we'll put in 52 Celsius, and that's how we'll stay for today's takeoff. We'll stay with a derated takeoff of 52 Celsius with climb 1 armed. So we know we're somewhere between 5 and 15% reduction in thrust. Let's complete some of the checklist here just to make sure the anti-ice is auto, the recall's been checked, flight controls are checked, ground equipment is clear, and the before takeoff checklist is complete. Checklist complete. And we're going to go runway heading to 5,000, V2. We can activate our V speeds now. Looks like V2 is going to be 169. We'll set that. And we'll be right back for takeoff. Okay, we're back for takeoff on runway 30 left at Minneapolis. This is actually current weather. You can see it's snow flurries at the airport. And we are set up for our derated takeoff at 52 Celsius. The runway is clear. There's no snow on the runway, it's just flurrying. And we got a flap 10 takeoff. And a couple things to mention on assumed temperature versus fixed derate. With assumed temperature, you could, if you needed to, which you shouldn't need to, but if you needed to, you could add power with using the assumed temperature method. And you won't have any control problems if you lose an engine. So on the takeoff roll, if you needed max thrust for any reason, you could simply advance the thrust levers to the maximum if you needed it for an emergency, like a wind shear or something like that. Airborne, you can get rid of the derate by pushing the toga switch once you're airborne, and that will remove the derated thrust and give you full takeoff thrust. Now, if you're using TO1 or TO2, it's a little bit of a different story, because with assumed temperature, your minimum control speeds, your VMCA speeds, are based on full takeoff thrust. That's not so with TO1 or TO2. It's based on that limit that you've reduced TO1 10% less, TO2 20% less. So if you increase the power using TO1 or TO2 and you lose an engine, you could run into a directional control problem because you could be below VMCA speeds. So generally with TO1 and TO2, we don't even consider increasing the thrust unless it's an emergency situation, like wind shear. With both of these, you shouldn't need to increase the thrust because your runway analysis charts, your dispatch papers, however your performance is figured, is predicated on the current weight, current conditions, current runway, and maintaining the segment climbs once you lift off. So what I'm going to demonstrate now is just taking off runway 30 left. Once we get airborne, I'm going to just say we need extra thrust for some reason, and I'm going to push the toga switch once we're airborne, and we'll just watch that the derate, which is the assumed temperature in this case, is removed. It goes to full takeoff thrust. Again, even if we were to lose an engine, we would still have plenty of controllability because we would have no problem with our VMCA speed. So with that, I'm going to release the parking brake, and we'll set 40%. I've got the sound switched off in this case, but we'll set 45% N1, stabilize, push toga, and we're going to go to our assumed temperature of 52 Celsius. So if I needed more thrust at this time, all I would have to do is increase the power, push the thrust levers forward, not push the toga because that won't do anything. There's 80 knots, our thrust is set, go to hold. There comes V1, there's V1, and we'll start our rotation. And with a positive rate, we'll get the gear up. So you'll notice as I fly away here, I'll just stay in toga. I won't go to heading select for now. 400 feet, we're going to go into VNAV. So you'll notice there's 400 thrust ref VNAV speed. And now let's say I need more thrust. I'm going to push the toga switch now and watch the derated takeoff thrust. It goes away, it goes to full takeoff thrust, and off we go. Okay, we'll get the autopilot on, and we'll go back to VNAV. we pushed toga, so we need to get back into a roll mode and pitch mode. So we've got a heading select. So we've got speed, heading select, VNAV alt, and we're starting to increase the speed. And we'll go to, once we start to accelerate here, we'll go to flap 5. Okay, we're level at 5,000 feet. We've retracted the flaps on schedule. And let's just take a look again at the thrust limit page. You'll notice that now the thrust limit page, the TO, TO1, and TO2 are gone. We've got climb, climb 1, and climb 2. And we've got go around, continuous, and cruise. And so these will automatically change as we continue to climb. Once we get to our cruise altitude, it'll change automatically to cruise. It may stay in climb depending on airplane option and configuration. Some airlines stay in climb, and some airlines will have a go to cruise. And then, of course, when you bring the flaps out of up, normally we'll see go around displayed on the primary ICAS. If we had an engine failure, it would automatically go to continuous in most cases, but we could come here and select whatever reference thrust we want, and you can see it changing over here. So that completes the discussion on the thrust limits and the thrust limit page along with the takeoff reference page, and selecting assumed temperature versus fixed derate. Okay, let's lower the HUD and go flying. Until our next briefing, keep the blue side up. Captain Al, out.